All right, we'll continue then. So, are there any other bonding environments for carbon? Here. Turns out there are. For example, carbon can form, something like this with a lone pair, or we have different arrangements. It can form a double and a single, a lone pair, etc. These are kind of strange species. They're going to be actually unstable potentially, or even a triple bond with a lone pair. All these are going to have a negative charge on the carbon, and the carbon's going to end up with an extra electron in order to have something like this. We can also have carbons with a positive charge like this. So let's say, etc. These are known as carbocations, and these are going to be very reactive as well. So, these species are more reactive, less stable. But here, carbon's going to be short an electron. Here, carbon's going to have an extra electron. That's carbon. Then we can continue on. Let's take a look at nitrogen as well. For nitrogen, what are we going to see? We're going to see nitrogen with 3 single bonds and a lone pair. We're going to see nitrogen with a double bond and a single bond. We'll see a nitrogen with a triple bond and a lone pair. But there are also other common ones that we might see as well. We might see nitrogen with 2 lone pairs like this. If nitrogen has 2 lone pairs like this, then it's going to have a negative charge on it because it'll have an extra electron there. Or we might see nitrogen with 3 single bonds like this. So to have a positive formal charge. And so we see this. This would be as an ammonia. This would be as an amide, NH2 minus. This would be as an ammonium, NH4 plus. Or analogs, it doesn't have to be hydrogens. We could have other atoms bonded there as well. So it looks something like that. Okay, that would be nitrogen, and then we could go to oxygen. See what kinds of bonding environments we have for oxygen. Oxygen is going to have 2 single bonds and 2 lone pairs. To have a double bond, 2 lone pairs. Typically we call this a bridging oxygen because it's going to bridge 2 atoms. Bridging O. This one we call a terminal oxygen because it ends there. Terminal oxygen. So bridging oxygen, terminal oxygen. And then we have other environments, like, for example, we could have oxygen with 3 bonds, but this is going to put a positive charge on that oxygen. We could have oxygen with 1 bond and 3 lone pairs. This is going to put a negative charge on the oxygen, etc. So these are common bonding environments that we'll see in Lewis structures here. We might as well just go down the list. After oxygen comes fluorine. For fluorine, we're just going to see a terminal fluorine like this. For example, we'll never see a bridging fluorine. So, for example, we'll never see a fluorine like this. Because that would put a positive charge on fluorine. And fluorine being the most electronegative species, electronegative is the ability to attract electrons, whereas electron affinity is the ability to attract electrons and to hold on to them. And so this one will be, so we'll never see anything like this, etc. We will, however, see fluoride, or fluoride and ionic fluoride, as well as oxide. I forgot to write that. In ionic compounds, oxide would be written like this. Minus. Nitride would be written like this. Net charge is 3 minus. That would be nitride. So we'll have fluoride here. Okay. And so those are typical, and so let's start with the just a brief review of Lewis structures, maybe some new topics in Lewis structures. So let me bring up the PowerPoints for these. All right, this is just showing the electronegativity difference because we write Lewis structures differently. We have Lewis structures for ionic compounds and Lewis structures for covalent compounds. And so that depends on the difference in electronegativity. In electronegativity, let's take a look at the previous slides here. This is the electronegativities. Fluorine's at the top, francium and cesium are at the bottom here. And take a look at it, the difference in electronegativities in the percent ionic character. If you look, the bonding is going to range from 0% ionic character, which means 100% covalent. So something like H2, Cl2, where you have the same atoms bonded to each other, will be covalent. And so if it's covalent, we would write the Lewis structure like this. This would be Cl2. And then if we go to something like HCl, HCl is about 20% ionic, which means it's 80% covalent. And so it's mostly covalent. We call it polar covalent. So we draw HCl this. Now, the electronegativity difference is going to tell us, how ionic the bond is. And how ionic the bond is how much the electron cloud here is distorted. That is, in chlorine, the electron cloud is symmetric like this. And both the atoms share the electron density equally. We can't pinpoint the electron, but we can come up with some electron cloud like this. Whereas here, chlorine's more electronegative than hydrogen. And so chlorine takes more of the electron cloud, or polarizes the electron cloud towards it. And so this would be the distortion in the electron cloud towards chlorine. However, this is still predominantly covalent, so we still say that there's a sharing. In fact, this is 80% covalent, only 20% ionic. Ionic would be no sharing at all. However, if we start bonding, like, let's say, potassium to that, take a look, or sodium, If we look at sodium, sodium is like almost 75% ionic here. And sodium chloride, yeah, it's predominantly ionic. Potassium chloride is very ionic. You can see up there, it's got high ionic character, like 80, 90% ionic. And so if we were to bond a potassium here, then there really isn't much sharing. It's just taking. And so in that case, we would write this as an ionic rather than a covalent. It's 80+% ionic. That means the chlorine's going to take all the electron cloud, and potassium gets really. It's not entirely the case because potassium doesn't give up completely. I mean, it's still about 10% covalent, so there's still a little bit of electron density that's shared, but pretty much we'd write it like this, you know, because what we're going to do is it's kind of hard to show, you know. Is it easy to show, you know, for example here, 80% covalent character? It's kind of hard to show that, so we don't. So what we do is we're going to do a dividing line here. The dividing line is this. If the electronegativity difference, this is electronegativity difference between the two elements is less than, let's say, about 0.5, then, you know, it's pretty nonpolar because it's pretty, you know, the percent ionic character is minimal, so we can say that's pretty much close to 100% covalent. If we have an electronegativity difference from about 0.5 to about 2, you know, then we'll say it's an electronegativity difference from about 0.5 to about 2 would be polar covalent, like HF. HF, you know, HF is still only 45% ionic. However, you know, this is not perfect. You know, what would the R squared for this correlation be? You know, R squared for this curve here, is it good? It's bad. You know, R squared is bad, so, you know, these aren't exact numbers. So the difference in electronegativity doesn't tell us all, because here HF has a difference of electronegativity of about here 1.8 or 1.9, and it's only like 45% ionic. However, cesium chloride has an electronegativity difference that's even smaller than HF's, and yet it's like 75% ionic. And so if we have an electronegativity difference of about 1.8, that means we have quite a big spread. It can be anywhere from like 40% ionic to 80% ionic. Do you see that? And so it's not a very tight correlation. And so these numbers, like if I said, okay, we're going to call anything with a difference in electronegativity of above 2 ionic, well, that's probably pretty safe, you know. But there are things that are below 2 that are still quite ionic, you know, and so we aren't capturing everything. These are not hard cutoffs, you know. A lot of people want hard numbers. They want, okay, what is it? What's the number? What's the cutoff, you know? Well, if you're in that category, you know, you're looking for a hard number, well, this isn't it, you know. You can't come up with a hard number, and so we're just going to come up with a kind of like a, you know, guess number. And so what we're going to say is electronegativity differences less than 0.5 are what we call nonpolar. Electronegativity differences between 0.5 and let's say 1.5 or 2 would be called polar covalent because they're predominantly covalent. However, all these are predominantly ionic. Do you see that? But we're just going to come up with a number. I don't know. What's the book's number? Do you remember what you memorized in Chem 4? Did you have to memorize a number in Chem 4? In Chem 4, I think they say electronegativity differences greater than 2 are considered ionic. Yeah. Well, that's safe, but that doesn't capture these, so it's not so safe. And so, this is not, but once we get into high electronegativity differences, these are predominantly ionic, you can see. It's not a great correlation. There's probably better way to do this. But that's just based on the electronegativity differences that we have. And so the way we're going to represent the structures is if we see electronegativity difference, like say above 2, or if it's a metal and a nonmetal, like here it's pretty easy. Metal and nonmetal, metal and nonmetal. Even though the electronegativity difference is only like 1.5 for lithium iodide, we'd still write that as ionic because it's metal and nonmetal. And so metals and nonmetals write as ionic compounds like this. But if we have nonmetals like HF, then we'll write it as covalent, even though the delta EN is pretty high here. You know? And so that should be safe as well. Okay. Even though when you classify it, I mean, if you had lithium iodide, you can see how it's only 1.5. The HF is greater. And so lithium iodide, you know, we'd still write like this. And HF, we're still going to write like this, with a line. We can see here the differences. You know, this is all polarizing the electron cloud here. And, you know, the red means what? Electron bridge. And so here you can see this is a lot redder than iodine. Well, iodine is a lot less electronegative, and so HI is much more covalent. HCl is much more ionic. But HCl we still treat as a covalent. We call it polar covalent because it's in the 0.5 to 2 range, so we'll call it polar covalent. This is almost nonpolar covalent, HI, but there's still a little bit of polarity. But you see the green here? It's pretty green. Here, there's quite a bit of blue here, meaning that there's quite a bit of positive charge buildup on the hydrogen. Here it's quite red, quite a bit of negative charge buildup on the chlorine. Here it's a little less. You know, we can see it according to the scale. These numbers here are for the potential. So we aren't going to pay attention to these numbers here. We aren't going to memorize those numbers there. The differences in ionic character. All right, so let's go to writing Lewis structures. This is just the same rules as in Chem 4. You know, all the valence electrons we count. We usually try to pair the electrons. Usually terminal atoms, we fill the octets first, or hydrogen only requires 2. Multiple bonds sometimes is needed. Well, that's just a kind of overview. Let's go to the actual rules for this. So we generate a skeleton. This is ethanol, the skeleton for ethanol. And there are different skeletons we could have done here. So those are called isomers, and those skeletons aren't any issue because we could do different things with oxygen. Here we see a bridging oxygen, but it's bridging carbon and hydrogen. This oxygen could have bridged 2 carbons. And so another potential skeleton for that is this. We could have had well, we don't have any lone pairs there yet, but we could have had this skeleton too. That skeleton's fine. That skeleton on the right is dimethyl ether. The skeleton on the left is ethanol. Both of those are isomers. You know, same formula, different structure. Both of those exist. Hydrogens, you know, are always terminal atoms. Central or bridging atoms are generally those with lowest electronegativity. So typically we try to put the most electronegative atoms in the terminal positions and less electronegative atoms in the central or bridging positions. Carbon atoms are always central. They don't have to. I mean, if you only have two atoms, it could be terminal as well. Generally, the structures are compact and symmetrical. However, not always. This one's incorrect unless we have to do this, because the oxygens, if you look at the oxygens here, this is called a peroxide bond. Peroxide bonds are one of the weakest bonds. These can be easily broken by visible light. And so this structure wouldn't be very stable because I think all frequencies, all wavelengths of visible light capable of breaking this bond. It's very weak. Oxygen-oxygen single bonds are very weak because of the size. It turns out that, you know, bond is a compromise between repulsions between the nuclei and attractions to the electron cloud. You know, what holds the bond together. And it turns out because of the size of the oxygen, the repulsions between the two nuclei here are significant. And it can't be overcome easily by the electron cloud here, which draws the nuclei towards the electron cloud. And so it turns out that oxygen-oxygen single bonds or peroxide links are unstable. And we try to avoid those, but sometimes you can't avoid them. Like in hydrogen peroxide, you can't avoid it, you have to do that. And so if possible, we avoid oxygen-oxygen links like this. And so this is another structure of this. However, the lone pairs are missing. I don't like that. You got to show the lone pairs. And then phosphorus has more than an octet. Phosphorus has something what we call an expanded octet. And they shouldn't have double bonded this yet. We don't double bond until we complete the octets to all the terminal atoms, which get filled first. But anyway, I'm just going along with Petrucci. And so this is the scheme here. We count the total number of electrons, we draw the skeletal structure, we place 2 electrons in each bond, identify the terminal atoms, complete the octets to the terminal atoms, subtract the number of electrons. So if we have any extra electrons, we place those on the central atom. But if we don't have an octet, then we're going to form multiple bonds here. This is standard procedure. This is the same procedure as Chem 4, so we'll spend much time going through it. And so let's look at NO2 plus. NO2 plus, nitrogen is 5 electrons. We have 2 oxygens, those are 6. And then we have a positive charge. Positive charge means we lost 1 electron, so it's -1. So it gives us a total of 16 electrons. And then we have 2 choices for skeleton. We could do ONO or we could do OON. OON. So let's do the other structure here. Well, you know, it looks like ONO is more symmetric, so that's a plus, but it doesn't necessarily have to be symmetric all the time. And so if we did an NOO, well, one of the things that would throw up a red flag is this, an oxygen-oxygen single bond link, but maybe it's not a single bond link. Maybe it's a double bond link. You know, that's one of the oxygen environments that I didn't show here. Here, you know, we have 3 bonds, but it could be 1 double bond and 1 single bond, like this. So maybe we have something like that there. Okay, then as we continue down here, we complete the octets to the terminal atoms first. So we fill up the octets here. Well, that takes care of all 16. We have all 16 taken, then that leaves no electrons left over. However, nitrogen does not have an octet. To complete nitrogen's octet, we'll take a lone pair here and share them, a lone pair here and then share them, so we'll get 2 double bonds. Well, I didn't know this. The editor missed this. Do you see something wrong with that structure? Yeah. Yeah. So somehow they forgot to erase this. I mean, if you take this lone pair and use that as a bond, then the lone pair is down here. We got to get rid of it. So it's too many electrons there. And so this would be the structure of this. Now, when we look at the structure of this, there's something we have to do in addition. This whole thing carries a net positive charge here, +1. And the net charge, there's 2 ways we get the net charge. One is given, of course, but there are 2 ways we can calculate the net charge. One, the net charge is equal to the sum of the oxidation states of all the atoms. Or 2, the net charge, actually both of these work, I should say and 2, is equal to the sum of what we call the formal charges. Well, let's try both. Tell me what the sum of the oxidation states is. Can you do the oxidation states in your head? Yeah. What's the oxidation state on this oxygen? -2. This is the same. The -2 and -2 is -4. What's the oxidation state on this nitrogen? Not +3. +5. +5 because normally nitrogen has 5 valence electrons and this structure has none. So it's +5. So +5 minus 4 is +1. And so the net charge is equal to the sum of the oxidation states. The other way of doing this is by formal charge. So have you learned formal charges? Yeah? Has anyone not learned formal charges? Learn? Okay. Well, formal charge is, did I talk about formal charge before? Yeah? What did I say about formal charge? Well, oxidation state. Oxidation state is what? How about that? You tell me what oxidation state is. Why don't you go back and figure it out so you can tell me, and then we'll talk about formal charge. What exactly is oxidation state? Okay, figure out what oxidation state is. If you were to explain to somebody what oxidation state is in your own words, what would they be? Okay, and then look at this. This is the calculation for formal charge. Tell me what formal charge is. A lot of people will tell me it's this equation, but that equation doesn't tell me anything. I want to know conceptually what formal charge is. And so look at that equation and then tell me what that means. You know, I don't want an equation for oxidation state. I want you to tell me, you know, verbally, what is oxidation state? The apparent charge on the atom? The apparent charge on the atom is what? What's the apparent charge on this atom? I don't see any -2 there. Is there -2 there? Or so you have to. It's apparent charge on the atom. How do you come up with -2? How do you come up with -2 there and a +5? How did this come out as +5? You got to tell me in words. The apparent charge is not enough. The apparent charge, apparently to me, it looks like there's no charge on there. It looks like the apparent charge is +1. I see that. That's obvious. +1, right? And so that's not descriptive enough. You gotta tell me a little more.